This video is an introduction to electric fields. We previously covered Coulomb's law, which calculated the attractive or repulsive force between two charges. You may have wondered how these charges know that the other charge is present. Well, each charge creates something called an electric field. This is very similar to a gravitational field. So in the middle of this drawing we have a negative charge, and there's an electric field that surrounds this negative charge. When a positive charge is placed within the negative charge's electric field, it is going to feel an attractive force towards the negative charge. And it makes sense that the further away from the negative charge, the weaker the electric field is going to be, and therefore the weaker the force will be on that test charge. Alrighty, so the variable to represent electric field is an uppercase E, and the way to calculate the electric field at a particular point is to take what we call a test charge and place that at the point that we want to calculate the electric field. The F in the equation is the force the positive test charge will feel, and the Q is the charge of the positive test charge. The units for electric field is Newton per Coulomb. And it is also important to note that the electric field is a vector, which means that direction matters. The way that you tell the direction of the electric field is that the direction is the same direction of the force that a positive test charge would feel. Negative charges then would feel a force in the opposite direction of the electric field. So we're going to work with this idea a little further on in the video. Let's do an example. A test charge of positive 4 microcoulombs is placed in an electric field and feels a force of 0.05 newtons in the positive x direction. What is the magnitude and direction of the electric field? So we know our equation for the electric field, and we know that the force a test charge felt was 0.05 newtons, and the test charge was positive 4 microcoulombs. And when we plug in these values, we see that the electric field is equal to 1.25 times 10 to the 4th Newton per Coulomb. Next, we're probably going to ask ourselves the direction of the electric field. We know that the electric field points in the same direction of a positive test charge feels a force. So our test charge was positive, so we know that the electric field is going to point in the same direction as the force. So therefore, the electric field points in the positive x direction. Let's do another example. What force, direction, and magnitude is exerted on a negative 10 microcoulomb charge placed in an electric field of strength 1.25 times 10 to the 4th Newton coulombs in the positive x direction? Alrighty, so we're going to use our electric field equation again. So we can plug in our values for the electric field and the charge. Alright, notice how we always just use the positive values here. Even though we had a negative 10 microcoulomb charge, we place in a positive value. And then we figure out we deal with the fact that it was negative when we talk about the direction. So we solve for the force, and we see that this charge would feel a force of 0.25 newtons. And finally, we have to find the direction of the force. We know that the electric field points in the same direction of force a positive test charge feels. And we know that the opposite direction for the negative test charge. So since this was a negative test charge, we know that the force must point in the opposite direction, and therefore it is going to be pointing in the negative x direction.